I think, yeah. Oh, we're good. All right, the
Okay.
recording is started. Go ahead.
All right, good morning, everybody. Today is our combined SOAR meeting. I'm glad to see that a few people showed up in the room. And Annie tells me there's quite a few online, so we are recording it, as Annie said, so for future use. Today, we're going to hit some modeling aspects and calling it Modeling 101. So we got a lot of technical stuff to go through. So I want to introduce Brad, and Brad's going to take over, and he has Colin with him today to kind of step through it.
Good morning. Yeah, I'll start off first, giving some brief update, kind of introduction to modeling and some of the components that are within SWIM. I'll talk through some of the submodels that we're pulling together for everyone's use. We'll then follow that up with the demo. So I'm going to try to get through the first step pretty quick. It's for those that are experienced modelers, I apologize. It's going to be very boring for you. For those that are learning it, I think hopefully that'll be helpful to you, but then we'll do some live demos. We'll do that both in PC Swim and EPA Swim, as we have folks that are using both of those programs. Jake and Colin will go through those. They have a couple things they're going to show, but that's also the opportunity that if you do have questions, please ask them during that time frame. If it's not what they're covering, that's okay. Ask the question, see if we can answer how to do something within either one of those platforms. Anyone that's in the room, if you have either EPA Swim or PC Swim on your machine that you want to follow through in our demos, that's great. If you don't have a submodel brought into those, let us know. We have a couple thumb drives here. We can give you a submodel to bring in so that you can follow along as we go, or you can just pay attention and watch the demos as we go. So people online, I guess it's hopefully you have a submodel you can bring in, and you can you'll bring that in now. So by the time we get to the live demo, you'll be able to follow along. So first question is, why do I need a model? Both our combined sewer systems and our separate sanitary systems have modeling components to your consent orders. For the combined sewer systems, obviously, we've had lots of discussions regarding your metric, which is a percent capture at the CSO outfall. That's determined during the typical year. That has to be calculated essentially through modeling exercises. And so it's on the separate sanitary side, paragraph 7A and 7B call out that you need to conduct flow monitoring program and field survey sufficient to update an H&H model for the system that are tributary to an SSO. Then once you have that developed, then you need to run a continuous simulation to identify the causation of your SSOs and to complete an analysis and identify an alternative that will address those SSOs so they can be eliminated. So where we started with all the models that we've been providing to all the municipalities is the Alcosan system-wide model for existing conditions. Keep in mind, a model is a tool to evaluate the system responses to rainfall. It includes the Alcosan system and a skeletal representation of the municipal collection systems. So depending on your needs, there may be times that you need to expand that model if you haven't areas of your system you want to evaluate further and it's farther up in the system than what's represented in the model. That just means you need to look to pull that information and expand the hydraulic representation. The models should be extended up to most overflows, or at least all overflows that were known by Alcosan at the time of the model developments. But if there's a new SSO that was identified, then again, that model may need to be expanded up to those areas. The model was calibrated primarily on the regional flow monitoring program conducted back in 2008, as well as supplemented with additional historical flow monitoring that was available at that time. This can be used to evaluate both your typical year system responses, like we've talked about for our percent captures. That's done on a typical year basis, but it also can be used to evaluate responses to design rainfalls. So let's say maybe our CSO doesn't activate for the typical year. And we're saying, hey, I might want to close that. Well, you probably want to look at some design storms to see what happens if you close it. So that all of a sudden you close it, you don't end up backing up Mrs. Jones' basement for a 2-year storm. So that's how that can be used on the CSO side. On the sanitary side, obviously those design storms can be used to characterize your SSOs and evaluate what needs to be done to eliminate those. Elksan did update the version of the model that we're using right now was updated to reflect 2020 conditions. What I mean by that is it was a completion of some planned projects. So when that was originally developed, there were some projects that were known to be happening. They weren't included originally because they weren't existing conditions. If those were completed, those were then incorporated. Those are projects, primarily Elksan projects or large municipal projects that Elksan was aware of and had sufficient data to represent within the model. Also includes a number of regulator modifications that Elksan has made within their system and revisions for the basin planner. Also at that time, they went up to the swim version of 5.1.012. And that's really the official version that everyone should be using for their simulations at this time.
The updated model that be released.
You're talking the cost priority model?
Yeah.
Yep. We're taking those and we'll get into that here today. But the question was, when will the cost priority model be made available? It's available now. We have to develop those submodels, so we're doing those on a per request basis. I know in the last 2 days, I think we've gotten around 10 requests. We're trying to turn those around within 2 weeks is our goal and our objective. So we're starting to work on developing those submodels right now.
Okay, so whoever needs that needs to send in a request.
Yep, and I'll touch on how to do that. So as we just talked about submodels, we've created some models, some submodels to make it easier to run these models. It's a subset of that system-wide model that Elksan uses. Keep in mind that to run the full system-wide model takes 2.5 days or so to run a typical year simulation. So why it's a very powerful tool, it is, if you're trying to only look at one little small area, it's takes a lot of computational power and time to do that. So by breaking the model up into smaller pieces allows that model to be run much quicker, now more in the range of an hour or a couple of hours to make those simulations, if not less for some of the smaller submodels. But that does require some boundary conditions to be put into those submodels. That's to account for, now we're clipping that model, so we're kind of cutting it to picture, we're taking a cookie cutter, cutting a piece out. Well, anything on the upstream end, we need to say what flows were coming in at that time. And anything at the downstream end, we're giving basically an elevation or a grade to use as a boundary condition. So that comes in with the submodel that we provide everybody. We'll provide those files to you, and those will vary based on the design condition that you're running. So there's separate conditions for typical year. There's different conditions for your design storm runs. So the first submodels that we developed were the existing conditions submodels. So that was, we developed those last year or a little bit probably before that. We distribute those on a requested basis. We also just recently came out with the cost priority submodel, as Jason presented at the last combined sewer system subcommittee meeting. We were able to negotiate with the regulatory agencies the ability to account for the Elksan regional improvements. So that's really accounting for the wastewater treatment plant expansion as well as the regional tunnels. We are in the process of creating those submodels now per request. We will do those the exact same extents of the existing condition submodels that we provided you before. So look very familiar. We're just going to have different boundary conditions, and it may have a few extra hydraulic components included in those to account for those regional improvements. So how do I get that submodel? So please submit the Elksan model request form to Three Rivers with a CC to Elksan. That request form is available out on the MBS site. The request should come from the municipality, not the engineer. And please email those to Annie and a CC to Sam Shamsi. Their emails are in the presentation here for those submittals. As you put those requests in, let us know if you're using EPA Swim or PC Swim. We package the files just a little bit differently depending on which package you're using, which we'll talk through some of the details and some of the differences of that in our live demos we'll do here in a little bit. Then we'll currently right now we're looking to transmit those through a SharePoint site. Link is sent to people that are identified in the model request form. We are maybe looking at a couple other options as well, so we may switch that up, but we'll make sure we're clearly communicate that to you in the email to you when your model is ready for you to download. So now what I would like to do is kind of do a deep dive into what's in a swim model. What are the different components that we're representing within the model? And again, if you're an experienced modeler, this is probably going to be a little boring for you. For those picking it up, hopefully this gives you a good foundation to move forward with. By all means, if there are questions, please bring those up as we go. First, I wanted to touch on the dry weather flow representation. So when I picture flows coming into the model, there's really two pieces. One is your dry weather flow on a nice sunny day like we have today. That's what's going through your sewer system. It's really made up of two components. Those are shown in the green and the light blue in the graphic. First is your groundwater infiltration. So that's what's leaking into your system all the time. That does vary by season and antecedent conditions, so it's not always a quite straight line as we're showing on here. If you zoom in to a short time period, it does look that way, but it will fluctuate much higher usually in the spring than what you see in the summer. You then have the light blue, which is your base wastewater flow. That's your sanitary flow coming from your residences, coming from your businesses, things along those lines. And then ultimately the dark blue is really your wet weather component that's making it into the system in response to the rainfall. This is inputted into the model currently right now. It's a continuous time series that blends both the groundwater and the base wastewater flows together. Then in order to represent the wet weather, obviously we need to have understanding what the precipitation is that we're looking for that response to be from. So we can represent rain gauges. The principal inputs that we put into that is the data type. Is it intensity for the rainfall or is it volume? The rainfall interval, hourly, 15-minute, 5-minute. The source can be an input time series or an external file. Then obviously you need to have a name. If it's an external file, you need names for those as well as for the internal time series. That rainfall then is read by the different types of subcatchments we have. And really the model has two different types of representations. One is for your combined systems. Those systems are basically taking the rainfall, it hits the ground, it runs off, gets into your catch basins, into the collection system. So with those are it's the area that's draining to a particular location in the model is what you would call your subcatchment. So that's discharging to a single location within the model. There's really two components of a combined system. One is your pervious area, one is the impervious. And there's different representation for those. For the pervious areas, that SWIM does have a number of different approaches that can be used for that infiltration. So it's basically looking at it, how much can infiltrate in the ground and not run off versus once that intensity gets above that infiltration capacity, then it starts running off and contributing to your system. A green amp, is that the primary one that's used within the model? I think there are a few that are using Hortons for some of the subcatchments, but green amp is the primary one used within the Elk Sand model.
Sorry, what's green amp? I'm sorry.
It's a routine for representing the infiltration in a pervious area. So if the rain's hitting the grass, how quickly can that infiltrate into the ground? And at some point, that's only going to have a certain amount of capacity. So that looks at different things of the different soil types. If it's a clay, it can only take so much versus if you got a sandy area, it can take a lot. So if I'm in a sandy area, it takes a lot of really heavy, intense rainfall to get runoff off of it. It's a clay area, doesn't take as much to create, exceed that infiltration capacity where I now basically starts acting as more of an impervious area.
Right, we shouldn't change whatever's default current existing. Model, we shouldn't change.
Right. So Glenn was basically stating that, should we change those, the methodology that's within the model? I would say you should keep the current methodology that's in there. Now, as part of a calibration, if you go through a new calibration process, it may be appropriate to modify the parameters of those. That would not be my first thing I adjust. But if you need that from a calibration perspective, that is typically a calibration parameter that is looked at. So if there's new flow monitoring data, that could be used for that.
And, there are some other subcatchment parameters which are much easier to measure on maps. So as Brad was saying, if you have new flow monitoring data and it does not agree with the model predictions, then and if you have the knowledge about your area that it has changed, usually there'll be more development in some subcatchments, especially bigger developments like a new mall was put somewhere. That should change the hydrology of that area. So things that are easy to calibrate and which are sensitive to flow are slope, width, and area, and percent imperviousness. That third bullet. The soil is the soil. If you had a certain kind of soil before, it's still going to be the same kind of soil later. But what could change is those four: area, percent imperviousness, slope, and width. They're easier to measure from maps or aerial photos. Right.
Right. So
Don't we want to keep it as renamed because?
yeah,
the idea-
methodology, I definitely would not change. What I'm saying is part of the calibration, and I agree, what Sam just said is the infiltration would not be my initial parameter that I would look to modify. There are other parameters that are part of your subcatchment representation that are much more sensitive and impact the flows greater. That's more on your impervious area side that I'll talk on in just a second. Those are usually your primary factors. The other one, as Sam said, you're looking for, was there a change to the collection system? So was there a redevelopment? Was there a new development in an area that may take away pervious area and now put impervious area? So the one area on the impervious side that I would say is probably the more likely thing to change would just be the area. So how much of area of pervious area do I have? The infiltration really is you're only going to see that impact on really, really intense storms. So if you're seeing a difference on your smaller events, it's not your infiltration into the soil that's going to make that correction. That's going to be your impervious parameters. So I capture pretty much what you're saying there, Sam. So if we look at those impervious areas and are a component of the system, those are the more sensitive things. So in there, we've had some issues online.
Someone's saying they can't see the presentation that's being shared. Jody was saying that the presentation may have froze, but when I asked that in the chat, people were saying that they could see here, but now they may be changing.
Okay. Let me know if we need to pause. But on the impervious areas, your primary things, as Sam said, are the most important ones are your area. The imperviousness or the DCIA are directly connected impervious area. So that's how much of your impervious surfaces are directly connected to the system. So sometimes I may have a road, obviously that's impervious, but if I don't have catch basins and that just slides off to the grass berm, and that's all it does, that's not directly connected. So that's where you can use some GIS features that estimate that. Versus the directly connected, it would be your roads that have the catch basins in it and things along those lines. So you can estimate that both from GIS. You can also look at your flow monitoring data. There's actually some pretty good ways of looking at your volume versus rainfall. And when you look at the intercept of, if you do a regression line through that, can quite often help you identify your DCIA as well. The other things that are sensitive are slope and width. You will notice in the model, there's, depending on where your system is, quite often the slopes or the subcatchments for the impervious areas are broken up in the slope categories. So high slope, medium slope, low slope, there's actually more categories than that, that then have their own widths and information tied to that. There are a few areas that just have one subcatchment represented with an average slope for that condition.
Those subcatchments are on top of one another. Like as you're saying.
Correct. Yeah, it's all one subcatchment. It's just in the model, it's broken up into multiple inputs. So the area is reduced for each of the area, but if you add up all those areas, it should match your total subcatchment. And graphically, what you're going to see in the model, you're just going to see a little rectangle, and they're all going to be right on top of one another. The other thing that could impact is your Manning's N for both pervious and impervious, but really your main calibration factors are typically your area, which is really not a calibration. That's usually, this is what it is. Your DCIA is a major one. That's usually the biggest knob that people are turning. Then a little bit on the slope and the width. Depression storage and percent and your depression storage and your pervious area representation are really pretty minor representations. That could also track with your precipitation, the snowpack and snow melt. It's also another capability of SWIM.
One more comment. That depression storage, and there's another one called initial abstraction. I don't see that listed here, but those two are good calibration parameters as well. And we recently noted that I think somewhere in Upper Allegheny, I forgot which area was it. Spinball or Sharpsburg area, as part of grow modeling. There was a subcatchment with cobblestone streets, and we were not matching new data with the old model parameters, and we were trying different things. It wouldn't just match. And when we paid attention to the pictures of the subcatchment, we saw cobblestone streets, which can kind of do a good job intercepting the runoff and create those puddles that will detain stormwater runoff. And when we started to change those, Andy was actually doing this and was frustrated, and I suggested try these two, and that's what I think was the trick in there.
Yeah, Sam brought up that quite often that depression storage or initial abstraction is another term for that, can be something you could identify as a calibration tool. He's seen a couple of places where, where you had cobblestone roads and things along those lines that will create quite a bit of ponding within your subcatchment, that can be a parameter that can be used to adjust that. Typically what you're going to see is if you're looking at detail, your modeled versus metered, you'll see a delayed response, which would be an indication of that depression storage may not be accurate. So if you're seeing that the response is happening too quick, means you might want to increase your depression storage. If it's happening too early, it may be something you want to decrease that initial abstraction.
That's more in Churchburg, kind of brick streets. That could happen.
Yeah. It could be anything that, if you go out, it can happen with old pavement too. I mean, it could be old asphalt that has a lot of potholes and things along those lines, or a lot of depressions. That can all lead to those same similar phenomena. It's basically where the water's going to pond first before I'll start getting discharge into the system.
Are you playing around with that now? That's more in Churchburg.
As I said, I'm not sure if it was one of those two areas.
But we did like road projects now.
Yeah.
I think what he said is just as an example.
Yeah.
Yeah, not 100%. If it was one of those two, may have been another, another borough or township, but,
Did I see there was a question
Yeah, there
online?
was a hand up. It went up and went down. So, hey, Ben Reynolds, did you want to ask a question? We're happy to make space for you to do so. If you just want to come off mute, we have speakers so we can hear you, I think.
You also got a comment online that potholes are a good
Yeah.
thing. They prevent accidents.
what did he say?
Potholes are a good thing, depression storage,
Yeah.
distributed storage.
All right, I don't hear.
Okay.
Let me know in the chat if you're talking, we just can't hear you, but let us know if you have a question. We're happy to answer it.
On the separate sanitary side of things, those are represented differently. I think most everyone's heard of RDII or rainfall dependent inflow infiltration. Basically that uses what they call an RTK method. The R represents the fraction of runoff. So what that means is the percent of the rainfall that'll make it into your collection system. So if that's 0.2, that means 20% of the rainfall is making it in. The T is the time to peak. If you look at the pink hydrographs, basically the RTKs really broke it up into 3 triangular unit hydrographs, one for a quick response, one a medium response, and one for a long response. The T is the time to peak. So that's for each time it rains, for each drop that hits, that's the time it takes to really get into the system. And then your K is the ratio of that time to peak to the recession of the hydrograph. So you have a separate R, T, and K for each one of those unit hydrographs. Those are all then added up together, and that makes your overall response. It basically takes each time it gets a rainfall. So if you got 15-minute rainfall, it takes that 15-minute rainfall, multiplies it by each one of these, gets a hydrograph, moves forward 15 minutes, takes the next rainfall, multiplies it by all these again, adds those up. So that's how it generates the hydrograph and the wet weather response for a separate sanitary system. Jumping in just to some of the hydraulic elements that are within SWIM, there's kind of what I would call the basic elements. Your node within the nodes category are just your junctions and manholes. So those are just places where pipes are coming together. Or sometimes a junction is more where there isn't a manhole, but you have a connection of 2 pipes together that are kind of a blind connection. You have your links, which are your conduits or pipes. But then there's specialized ones for both nodes and links. For the nodes, I would call out kind of the storage and an outfall. And I'll talk through each one of these in a second. For the links, you have more of the things that you would see within a regulator with your orifices and weirs, an outlet link, as well as a pump link to represent a pump. Looking at the junction of manholes, they're basically representing the model as a cylinder with a default diameter of 4 feet. That is something that's user defined, so you can change that. It basically talks, those are put in where you have 2 pipes coming together. Those are your places where you can load flow into the model. So flow is loaded in at nodes, not links. They can be pressurized, or flow can be lost through flooding of the manhole. So you can set it up where it's a sealed manhole, where HCl can still come above that manhole, but it's not going to be lost in the system. Or you can represent it if that's just our standard lid blows off, water comes up to that level, spills to the road. So it can be represented either one of those. You can also represent in that condition where you're allowing it to flood the grade. It's an area that goes to a road that that'll feed back into the collection system after the system goes back down. You can actually represent a ponded area on the surface, so that yes, it's lost to the ground, but then as the HCl in the system comes back down after the event, it will drain back into the collection system. So your main input parameters are your name, your invert elevation, the depth. So it's basically the invert plus the depth is going to give you your rim elevation. The ponded area, as I mentioned, if you want to be able to track that flow, if it floods out of the manhole, and then also if there's an external inflow coming in at that location.
Brad, on the, and I apologize if I missed this, but for the pressurized part of it, we use surcharge depth for that.
Yes.
That's okay. So that's kind of the standard way you would represent a lockdown manhole would be to add a surcharge depth.
Correct.
To it.
That allow that HGL to rise up above that manhole.
Depth going from the rim to the invert.
Correct. Yeah, it's basically what you're putting in here is your invert. So that's the lowest point within that manhole. And then your depth would be the distance from there to your rim elevation. So that wouldn't be to your surcharge depth, that'd be to the true rim elevation.
I think there is a setting where you can change how you handle depths and inverts somewhere. Not to confuse anybody, but if for some reason you're only entering your rim elevation and then there's a depth, it'll calculate the invert elevation for you. I think that you're aware of that.
It's both ways.
Okay.
There's
Yeah.
a choice that you have as to what you want to be inputting, and both in terms of the rim elevation that you want to put in or the depth that you want to put in. So that's an option that is present when you're creating a model. But the way the AlkaSam models have been built, and this is more of a demarcation in PC Swim that it is showing you both the depths as well as the rim elevation. In terms of input, what you're providing is the manhole depth, and rim is a calculated parameter within them. The other thing that Jake was pointing out in terms of surcharge depth, surcharge depth is actually a distinct parameter as compared to your rim elevation when you're working with junctions. So in junctions, you put in the manhole depth, it works out the rim elevation, but there's another parameter where you specify the surcharge depth. So it is just modeling a lockdown manhole, which is going to allow the HGL to rise above the rim. When you're working with storage nodes, it has a single place where you mention the rim, so to say. So there you are going to work out your surcharge depth and then put that thing as your manhole depth. So there are no distinct parameters for rim elevation and surcharge elevations. When you're working with storage values, storage nodes, there's a single value that you need to work out.
Good segue into the storage nodes. So storage nodes are used to represent, obviously, storage. So it could be representing an EQ tank. It could be used to represent a wet well. If it could be a large diversion structure that has a significant amount of volume within it. Those are all different things that you can use a storage node to represent. The volume is described as a function or a table of the surface area and the height to define that. So you can define, it doesn't have to be a square or a rectangle. So you can define for each depth of flow a different cross-sectional area that's being provided with that storage. So you do have a lot of flexibility with that. That's kind of shown on the graphic on the right-hand side, kind of how that would be done. You can lose flow through evaporation. That's an option to identify within here. So if it was going into an open storage tank or something along those lines and you want to account for evaporation, you could do that. Your primary parameters are the name of the element, the invert elevation, the max depth, that curve to represent what that storage is, identify if you want evaporation, and then you can also have flow coming into those locations as well.
I have a question on that. And Colin, I'm glad you brought it up. I was always frustrated with the fact that I couldn't put a surcharge depth on a storage. And, the fact is if that's locked down, it's not going to flood out of that structure. It's going to push, I guess, flow further upstream. But you're saying that the appropriate way to do that is you're just adjusting that depth.
Yes.
Okay.
Outfall nodes, these are the ends of your collection system. So this is would be at an outfall. It could be in our submodels where we're clipping it, where it's maybe discharging in the interceptor and we clip the model at that point. That is now an outfall. It's only a single link can be connected to that outfall, so you can't have multiple pipes coming to it. It can be designed downstream boundary conditions. As I mentioned before, when we create the submodel, the connection point to wherever the downstream end where we stop the model, we do put a level boundary condition in that represent whatever the HGL is and the pipe that it's discharging to, so that it's accounting for those downstream conditions properly. For many of the outfalls that are going to the receiving waters, there is a boundary condition within the model to represent those river levels, primarily along the main rivers. One of the unique things of the Pittsburgh region is many of those outfalls were built before the navigation dams were put in. So as soon as the navigation dams went in, the outfalls, many of those outfalls are submerged. So it's not the elevation of the outfall pipe that controls when you can discharge the river. It's actually the river level. So it's very important for those conditions to put that boundary condition in. There are some boundary conditions in for some of the upstream trips, but not all of them. So that's something to think through. If you know of a outfall that is impacted by the response within the stream system or river system, and there's not a boundary condition, that may be something we might want to look at adding. The question is there data available to do that? That's one of the challenges when you get in the tribs, is there's not always available data to do that.
Where do you see that boundary condition in this example, K67?
That the last two parameters that you see, the type as to what kind of a boundary condition you're providing, which is a continuous time series,
So it's in the time series.
Yep.
and then you provide the name of the time series.
Jake, remember when you were looking at the Turtle Creek model a couple of weeks ago? And I said, free outfall boundary doesn't make sense. Let's just put some boundary just chop off the height, the time series to the depth of the intercept. Now, this option, I didn't remember at that time. Normal flow depth in a conduit, that's what we were trying to accomplish. So, so sometimes, you know, that will be another way to do what we were doing. I just thought about it.
You can just select normal flow.
Yeah, I think so. There is a drop down box.
I think in the type here is
Yeah.
where you can select that.
Yeah, so it will be time series or free or normal flow depth or fixed stage. So we are going with, you know, either the fixed stage or a modified time series, but normal flow depth would be, you know, quicker way to look at the same.
Yeah, I believe I tried fixed.
What are we doing, Turtle Creek?
One of the things we're discussing here, just to kind of get the folks online caught up, Sam was talking about an analysis that he was working on with Jake in an area up in Turtle Creek. And they're looking to try to represent a downstream boundary condition. And they're calling out that there are some options here that if you don't have, say, a river or a stream gauge in the area, you could represent other ways of either free or normal flow depth in the conduit or a fixed stage. And you can do that through the model here. So it gave some other options that they could use to try to evaluate that downstream control.
And I think in general, I think Sam was concerned that just using free flow.
Right.
A realistic approach. So
Yeah.
take out the Turtle Creek thing. I think what Sam is saying, if you want to look at something like that, you should look at this box. We'll look at it, the normal.
Yeah, I've never played around with that parameter.
So you're saying that could be another option, Sam, what you're saying, look at that, see what that is.
So you're playing around with that time series.
No, you're, instead of using, if there's not a time series, or if you don't want to use the time series, to put a different type of boundary in. And down here in the type, instead of picking time series, you could pick one of these other approaches and use a different boundary condition
I
there.
got you.
So the thing is like the Alphasan model, wherever the information was available, it has been incorporated into the model. And that is the information that should be used. But when you're running into a free outfall condition and you know that that might not be a representative situation, then you have the option of adding information. You are enhancing what is already present in the model. And that is where you incorporate any information that you might bring to the table.
Or if you're going through another place where I can see where you might want to modify this is, let's say you're going through a calibration. Okay, so the time series that are in the model right now are for your typical year time period. Well, obviously, if I'm doing a calibration and I know, hey, the Allegheny River was at a flood stage during these events, you may want to put a different boundary condition in there to reflect that, to account for your overflows properly.
Yeah, not to belabor, but I think what Sam was, what we were looking at that particular model was when the community was saying, I can't, no matter what, I can't get into the system, right?
Yeah.
And I think so, what Sam was saying is we need to look at something essentially maybe different than free flow, because that's not realistic. You're going somewhere. So that's where you're saying, maybe look at this normal part, right, Sam?
Yeah, if you, this is in the context of looking at different planning scenarios. Suppose you came up with a project in your community and you wanted to evaluate the performance of that project under different operating scenarios. There are two extremes of looking at that scenario. One is free outflow. As if Alcosan gave you unlimited capacity in their interceptor. You know, I mean, it's pretty much an academic exercise because we cannot give you a free interceptor connection and say that there is no flow there at all. You know, nobody can, not just Alcosan, nobody can give you that kind of assurance. The other extreme would be that it is full all the time. And sometimes municipalities say that, hey, your interceptor is full all the time. So no matter what kind of project we create, we cannot get that kind of flow into your system.
Right.
So the good news is that we are lowering our HGL by virtue of expanding our treatment plant and putting new tunnels, which will lower the HGL.
But you're not doing that out the Turtle Creek system. Not lowering that HGL.
That is true, but there are other projects down the road, you know, which we call the selected plan. So there are other options. If you want to look into that future scenario, we don't have an HGL ready for that for you to model. But you could kind of simulate that situation by lowering that HGL yourself. Or just put that normal flow. Normal flow boundary condition would mean that our interceptor is to its capacity. It's carrying the flows that, you know, it should, but it's not surcharged to the top of the manhole.
Okay, I think we just don't want to get into specifics.
Okay, yeah.
I think what he's saying is, there's just another way to look at it.
Yeah.
And see what that reflects in the model. I think that's what Sam's saying,
Yeah.
right, Sam?
And people were able to hear that.
Yep,
so,
good.
you know,
Thank you.
About that
Yes.
series name, do you want to keep that exact format that it was written out as?
For the typical year stuff, I would say yes. There shouldn't be a need to change that. Now, if for some reason you're going through a calibration, like I said in the example where you know you're at a flood stage, so you're trying to account for that, by all means, that should be a different name. Because you're not representing that same thing. But for the typical year simulation, as Kyle had said, a lot of work has been done to create those to represent the typical year, and I don't see any reason why those would change for that time period. But if you're trying to simulate a different time period, by all means, you should create your own time series for that with its own name, so it doesn't get confused with this.
Run a different storm then. 5 years.
But even the 5-year, 10-year, and again, what has typically been the recommendations is there's certain timeframes to run that within the typical year. And we're basically assuming a normal pool elevation for those boundary conditions. So like I said, it may be a submerged outfall. We're still assuming a boundary condition. But what you typically see, at least on the main rivers, is your time of concentration within the collection system is so much faster than the time of concentration within the Allegheny watershed. You're not going to see that river come up during your storm event for a 2-year. Now, does that mean you can't have a flood stage that already happened and get hit with a design storm? Yes, you could. If you want to evaluate that, then yes, you could maybe put in what my recommendation was, take the time series out and put one of these steady boundary conditions in for that type of condition if you wanted to evaluate the impact of the system on a different flood stage. So looking at links, conduits and pipes, these are your main elements to get flow from one node to another. A couple things I wanted to highlight is you can represent sediment within those. We all know many of these pipes are very old. There has been some sediment built up in some of them, so you can represent that. And the bottom part of the pipe is shown in the graphic on the right. Your main input parameters, again, are your name, your inlet and outlet nodes, so your upstream and your downstream node for that pipe. Offset at the inlet and outlet. So again, going to elevations, your node has the invert elevation. Here you're putting an offset to that invert elevation in the node. So if that pipe comes in 6 inches above that, your offset is 6 inches. If it comes in right at the invert, that means it's 0. Obviously you have your length, your Manning's N, your roughness coefficient for the type of pipe that you have, the geometry of the pipe. You can represent all kinds of different pipes within SWIM, not just circular, not just box. You can make ovals, you can make all kinds of unique geometries within there. You have your losses, your entry, exit, and average losses, and the other is a presence of a flap gate. You could do this on that outfall node that I talked about before. So if there is a flap gate that keeps the river from backing up or flow from backing up into that pipe, it's a simple flap gate yes, no type of input parameter.
So that's not, the flap gate's not on the outfall itself.
You can put it in many different places. So yes, you can put it on the outfall. That's a place. You can put it on a pipe. You can also put it on an orifice, a weir. There's lots of different places where you can put that flap gate.
If you put it on multiple things, so that's zero things in.
I have found some places that SWIM does struggle with that at times. So if I have a flap gate at the very end of the outfall pipe and I have another flap gate up at my regulator, and there's 100 feet of pipe within those, sometimes the HGL between those two gets a little funky. I try to represent it where it truly is. Now, if you actually truly have 2 flap gates, maybe you put them in there. You can look at your runs and see if it makes sense, but I would look at that closely. If it's causing problems, I would get rid of one of them and figure out which one is the more important one to get rid of. Yes, to some extent, it kind of depends on your system. Maybe times it may be more accurate to keep it at the regulator so that, because what will happen if I fill the pipe with water, right? So let's say my river elevation's up here, my outfall pipe's down here. I have a storm event, it's going to fill that outfall pipe and it's going to stay filled because it can't exceed the elevation in the river. But if my weir is below this elevation, that water's going to flow backwards back into my regulator. But if my flap gate's back there, that'll keep that from happening. So it is something you kind of have to look at site by site basis. But that's a great question. That's something that we've kind of hit on more in the last couple of years where we've seen some issues with having multiple flap gates.
And when you have a situation when you have 2 flap gates, look at the drawings. Go and hunt for that drawing, look at it. It may have been a mistake or an oversight. Because some of, these models originated as conceptual planning models, and we have improved them since, but maybe there is still places for improvement. So make sure that there are actually 2, one in the structure and one at the end of the pipe at the river, but that's unusual. So that's why I'm suggesting, look at the drawing, maybe you can eliminate one if that's not.
If you don't have the drawings, go look at it in the field and see if you can find it. Now, sometimes, as I said, sometimes they're submerged, so it's hard to see the one at the receiving water. But that's another way to check it just in the field. So looking at another type of link, a specialized one is pumps. There's actually 5 different types of pumps. I'm not going to get into all of those here today, but they are listed here. Your main input parameters are the name, the inlet and outlet, nodes, name of the pump curve. So you basically you can put curves in for how that wet well reacts to the flow and how it's pumped out of the system. Your initial on-off status, so is the pump running or is it not? Or does it need to hit some condition to start? Then you put your start and shut off levels for each of those pumps. You can represent multiple pumps within the wet well. So if you have a pump station that has 2 pumps, you can put 2 pumps in. You have for the other places, you can put more in. Other times you may want to just put a composite pump curve in, depending on the unique nature of each one of those. Most of the pump stations that, at least that are in the model now already have pump representations in there. If it is a municipal pump station, you can take a look at those. If there's been changes to how those are operating, that could be something that could be looked at and modified. Links, orifice, so that's representing an opening in a wall or a plate. These are typically at your regulators. They can be circular or rectangular. They can be located at the bottom, so on the where it just drops through a hole like in your bathtub, or it could be on the side orifice. They can have a backflow preventer or a flap gate, as I just mentioned a couple seconds ago. You also see in the model many times those may have variable conditions to them. Many of the Alcosan regulators are represented with variable orifices along the main rivers. There's basically a tipping gate. So there's a plate that actually changes its position depending on how much flow is going through those. So there's control rules that kind of define what that does. So that allows you to adjust that orifice opening based on hydraulics. So you put in your name, your inlet and outlet nodes, just like the conduits. The configuration is a bottom or a side, the shape, circular, rectangular, the height above the invert at the node, the discharge coefficient, and again, does it have a flap gate? Weirs, again, usually located in diversion structure. There's 4 different types that can be used. The transverse, side flow, V-notch, or trapezoidal. They can be allowed to surcharge or not, and also can have a backflow preventer tied to them as well. Again, you have the name, inlet, outlet nodes, what type, the height and the length. The height is actually the distance from the top of your weir to the top of the structure. So it's not from the invert to the top of the weir. That is actually your crest height.
What's transverse?
Transverse is,
The direction of.
yeah, it's basically your flow's coming in right into a weir straight on.
Yeah.
Versus a side weir that's coming in, maybe you have an orifice that it's going straight into, but then you have a side weir that's running parallel with the pipe. So you also have your discharge coefficients, and again, whether you have a flap gate, outlet, as we mentioned before, this is really at the end of the model. So this is at an outfall pipe or at a cut in the model at the downstream end. You can use rating curves there for relating head and discharge. That's not used very often. I think there might be one location in the Alcosan system-wide model that does that. You can have a backflow preventer at these locations as well. But most of those are going to be pretty simple. It's just the name, the inlet and outlet knows whether it has a flap gate and the inlet offset. Now it might also have those boundary condition thrown in there. Yep.
What exactly is the inlet offset?
So inlet offset that's going to be, again, that's defining your elevation of that pipe. So again, the elevation's at the node. So this is basically saying this is coming in. Is it coming in at the invert of that node? If it is, it's 0. If it's coming in 6 inches above that invert of that manhole, then it's 6 inches. I think typically for outlets, those are gonna be 0 typically, because then
What's happening at this particular location is that we are trying to model a ductile outflow. So just think of it as an overflow pipe, which is at an offset. But to control how much flow you are allowing to get out of it, you're using a rating curve. So that rating curve is what is being modeled as an outlet. So you still need to model the offset of the overflow pipe, So that's the inlet offset. And then you are applying a rating curve to control how much flow you are letting out of the.
So I take my statement back. That is not always zero on these. It's again, it's just like any of your other conduits. It's at that upstream manhole. What's the elevation of that pipe that's leaving? Or the flap gate or whatever that you're representing with this element.
Do not put a boundary condition on it out though.
Yeah.
Because you are essentially incorporating that functionality within the control or within the rating curve that you are putting in.
But it wouldn't be a time series. It's just a different way of representing it.
Yeah, so this is not, we had the out. The others are just, the other ones are just conduits and you're not using an outlet. These are very unique for the outlet. There aren't, like I said, I think there's only one within the Alcosan model that had those, and that's at A68. And I think that, so that's the only location where that's at.
Yeah, don't confuse outlets with outfalls.
Yeah.
Our asset management system, which is called IAM, Info Asset Manager. In there, outfalls are called outlets. So be very careful, like our GIS folks were a little confused with that. So, in stream, outlet does not mean an outfall. And it's very specific to only storage nodes. As Brad mentioned, there's only one out of, 10,000 nodes that we have in our model. It's very unique situation, and I'm pretty sure most people don't have to worry about an outlet.
So those are the main elements. Just step on, I'm going to go through these very quickly. These are for your submodels that people are requesting now for that cost priority model. This is the process that we followed through last time. Like I said, we are looking at this and we may tweak this, but as of right now, this will be the approach that we'll use. You'll get an email from Annie saying that a link is going to be sent to you. The second email will contain that link. Once you get that, you'll have to ask for a code. It'll send you that code. You'll put that in and then you'll be able to download that file, basically hitting the open. The one thing that you will get is in the past, when we did the existing conditions model, we kind of first sent you the typical year, then sent you the design storms separately. We're going to package that all together in one.
What comes from this value?
Yes.
What engineer to get it correct? Put both the municipality count in.
The request comes from the municipality, but they can list who they want it sent to.
Okay.
So that way the manager doesn't want to download these things, and we understand that. So that wasn't the intent. So the manager or someone from the authority or municipality will request it, but they can identify you as the person who received that model, and we'll send you that notice. Yeah.
Yeah, I've been including the manager no matter what,
Yeah, it's.
because technically they're the owner of the rental,
Right.
So, it's their responsibility where it gets distributed, but often, as you see, especially in the new forms. And, your firm just submitted them. You guys had both the engineering firm and the manager, so both those individuals would be good.
With those, you're gonna, as I just mentioned, we're gonna put the design storm and the typical year information all together. So you'll get one model that'll include your typical year run already in it. So that'll have your input files. It's gonna have your output files, report files, your climate, rainfall, hot start, inflow, boundary conditions, all the stuff that you need to rerun it if you needed to, but it's really gonna already come in as run. So you'll be able to look at those results right away. We'll then provide the additional design storm information. Remember, we'll provide that for both winter and summer conditions. That will really include a rainfall file, a boundary condition files for the downstream levels and upstream flows, as those will be different for those design storms as they are for a typical year. Then a modified climate file for the winter design storm when you're running that. So again, we'll package that all together, simplify that a little bit from the last time.
All right, the inflow file they get, is that like a subset of the whole inflow file?
No, it's the full info file.
So that file is 3 GB. the down, the folder sizes that I've seen, they're usually not that big. So do you zip that?
Yeah, we do. Yeah, we do zip it. So we do one of two things. That's where there's a difference if you ask for it in EPA swim format or PC swim. This PC swim is the .pcz file, which is a zip file within PC swim. If you're asking for EPA, we use a standard zip file and put it all into that. All right, with all that said, Jake will come up and kind of run through a demo of PC swim and walk through some things there. If you got questions as he's going through that, by all means, let Jake know.
Thanks, Brad. Okay. Let me get to this. Maybe we stop sharing.
Press escape, it's still in the preview mode.
Yeah, escape.
Yeah, don't stop sharing. But you will have to do that again. Not here.
Escape's not doing it.
I think so. Almost sure playing.
Better. Okay,
All right, we are seeing a desktop.
all right.
Be sure to go with just PCs.
We're gonna do PC swim first and then we'll do an, yeah, regular swim version after that. Okay. Is the McLaughlin run one on a different drive? Apologies, guys. For this. Let's find that. Yes, yeah, you'll see similarities throughout this. Kind of want to highlight those. Now, when you request the model, when you get the download information, you know, it does depend on which PC swim or swim you select, and you'll get a PCZ file or a zip file. So, for instance, here's C5310 submodel. It's a PCZ package, and Brad had shown on this slide everything that's packaged within there. And then there are design storm files that go with that. So I'm just going to select the package file and open that first.
So it's 670 megabytes. You know, 667 megabytes to be precise. So what I'm curious, like after it is unpacked, what will be the size of the inflow file after it is unpacked?
Well,
So I thought you were clipping it and
No.
giving them a smaller file.
the thing is like it's a text file, so zipping it actually makes it really reduced. So from 2 gigabyte, it becomes like 300 something megabyte.
I know, but I didn't know if PCZ was doing the same thing.
Right, it does.
It does.
Mine packaged it to your downloads folder.
Page guy. Unzip all of these files.
Well, if you're making use of EPS swim, then you should wait for my time.
Yeah, ignore this.
Nobody ignored it.
But you're gonna be using, probably using PC swim also at the office, right? Potentially. You can always go back to the presentation.
You can get a 30-day free license. Finish your project in 30 days.
Yeah.
That's somebody else.
It would take me at least probably 3 months.
Yeah, exactly, Dave.
Representatives of PC Swarm are listening. We're all.
Hi.
Or provide a sponsorship. How about that? Jake would like his YouTube channel. be sponsored by
Yeah.
PC's.
Works. It's Three Rivers YouTube channel.
Yeah, that's true.
All right, we're making moves here. Maybe I clicked on it too many times.
You want
I have a tendency to do that. Okay, it's open.
So be patient. Some of the files are large, so they do take a little time to open.
So here's an example of a submodel, unpackaged, you know, really just clicking on that PCZ file. I guess that's a benefit of PC Swim is that it has everything packaged appropriately, that you're clicking, it's extracting all the files to the appropriate location and mapping them all together. So they're all linked. And when you get your typical year model, the results are already up to date. The results are built into the model. So that's a benefit there because it's going to take you a lot longer to run the typical year model than it would a design storm model, for instance. But as part of this demo, what I was going to do is kind of run through the process of running the design storms, because it shows you how each of the input files interacts with PC Swim, that kind of thing. So a few things to note is there's a standard naming convention for these models. You can see it up at the top that gives the year, the month that it was developed, what would it be? The sub area? What do we call the planning basin? Planning basin it's in.
POC often is right in that spot. So
So it'd be planning basin first, which would be Chartiers Creek, then your POC C5310, Three Rivers wet weather submodel, existing conditions, typical year. I'm the one who actually clipped this model and put it together as part of LSSE. So you kind of want to keep to this standard naming convention. So if I'm going to create, for instance, my 2-year winter design storm model, I'll be changing typical year to WDS to YR. So winter design storm 2-year. The notes over here should also be updated to reflect that. So first thing I'm going to do is I'm going to save as a new model here. And I also want to say that the running of these design storm models, there's a whole presentation on that on the MDS recorded that you can watch. I think it's on YouTube as well. It goes through specifically this process. So I think actually I'm going to keep those notes the same. Sam, do you have any objection to that?
Click on add button on top. And put, like Jake running that. Converted to clear distinct design. So. That's documentation, it will be very helpful for you down the road, but especially for us. The changes you make to the model, every time you change something, click on that plus button. Write down a note there. You don't have to write your name or date or time because that is automatically assigned to it. The program knows who is using the model and they will put their initials. So, though you put JCB there, because Khalid Khan is logged in, so look in the note, it's actually his name there. So.
Yeah, that's a good point. I had always thought we were revising these project notes, but you can continually add notes for, okay. And
That's your journal.
And part of that discussion will take place with the ad hoc committees when we're talking about, what model revisions we're doing. I think, it's kind of a teaser to future presentations and meetings with the ad hoc committee on that as to how we're supposed to document all this.
Like that question that Marissa was asking earlier about 2 flap gates. If she finds out that there's just one, the model was incorrect because it had two flap gate. If she removes one, she goes here, puts a note that, the redundant flap gate was removed by KLH, and that's all you have to say. The date and time and your initials will be stamped on it automatically. So it's almost the same as, as if you're entering your timesheets into your system.
Okay.
Logging everything you are changing.
All right, so to continue here with this winter design storm run, first I'm going to go into rain gauges. You can see here's all the rain gauges linked, currently within this package. I am adding a rain gauge. And wait. Do I just import the rain gauge? The rainfall file.
Or if it's a text file that is already.
Yeah.
You still have to give it.
This is the way I've done it before. So I'm going to,
As you quickly saw, Jake just changed that increment to 15, and that is what most of the range gauge data is saved on the website. So that can be important.
so the rainfall file is on my store and go here. Here's the C5310 files. I want to extract so I can access the. Okay. So here's 2-year summer, here's 2-year winter. These are the boundary conditions and input files that are associated with that design storm. So this 2-year 24-hour rainfall DAT file is what I'm trying to import into Swim, into PC Swim here. So I'm going to go back. Get rid of all these other instances of Swim I have open right now. I think I can import from that file. Oh, that's what I'm doing. Okay, got it. So here's my winter 2-year design storm precip file. Assigned to that rain gauge. Okay. I think there's different ways to go about importing that precip file, but now that I have this rain gauge, my name. Actually, apologize for any confusion here. This is the way you could do it differently. Don't confuse this too much, is you can change this file name and actually import the .dat file into there and then copy that down to all the rain gauges. That may be the way that I think Amanda had done that for the YouTube presentation.
Yeah, there was a previous presentation that you could take a look at that talked through some pretty efficient ways to go through and modify that. You can do that either through PC Swim, or you can also sometimes do that through the input file as well to affect that with our different programs.
Yeah, so instead of adding a rain gauge, I just changed the rainfall for these rain gauges to represent the 2-year file. So if I do that just for one, then I can go into my table for the rain gauges and copy that file name down, paste. Okay. So that way I'm not reassigning rain gauges. All right, so that's the appropriate way to do that. All right, so next, so that's our rainfall. Next, we need to look at boundary conditions. So the files that are provided. We already went through rainfall. This climate file is specific to winter design storms. Any other files are going to represent boundary conditions. A head boundary condition is going to be, our depth downstream. At an outfall, a flow boundary condition would be if we had to cut the model from the upstream, you would apply that flow time series upstream. So in this situation, we have one boundary condition that needs applied, and that's at C5310. So as I'm going here to my outfalls, see our outfalls with their downstream boundary conditions. This is the connection to the Alcosan interceptor. I'm trying to think of the right way to determine where you need to apply these. This is specifically named C5310 underscore TY for typical year and ahead. So that's the boundary condition of the connection to the Alcosan interceptor, representing typical year rainfall. Now we need to plug something in there that is representative of the 2-year winter design storm. So we're going to import that time series. I need to apply that time series somehow. I thought I could just change it here, but
Make a selection and say assign to this node.
I need to bring it in, don't I?
Right, so this is here.
Okay. So I loaded it in.
Yeah,
Signed out. Okay. Right there. Okay.
all right, we'll talk next week.
Thing to keep in mind
So we'll
is
talk next
you're only
week.
changing where we clip the model is the boundary condition we need to change. You don't need to change all the ones that are on outfalls going out to the receiving waters. Those stay the same, whether you're running a typical year or a design storm.
So our river boundary conditions
So
are
you can
staying the
only
same.
have 1, 2, maybe 3 or so locations you need to change. It's gonna be a head boundary condition at the downstream end of your submodel where.
Good, how you doing?
Interceptor, or into a trunk line. And you may have upstream flow boundary conditions that would need to change. This particular one doesn't have that, so.
I think we had some comments online and we weren't able to hear.
No, yeah, I was gonna say, I thought I heard a voice. I didn't see anyone's microphone turn on. Have those speakers up as loud as they go. I don't know, is your system sound all the way up though? Like the microphone, or the,
But it's only coming out of here. It's not coming out of there.
I'll
Yeah,
take
we have,
it.
yeah, if we have questions, I type them in chat and we can go through them. All right, so we went through signing the new rain gauge. We revised the boundary condition. For winter design storms specifically, you need to revise the climatology file. So under climatology here, we're referencing an external climate file for the typical year. You need to go in and under your winter design storm file, select the modified climate file there. Next, we're going to go into our simulation options. And this is where we need to change the dates that we're running this. So currently this is running for a full year. This is the typical year for 2003. So guidance is given. I'm sure it's in several places, but as far as the dates we want to run summer design storms for, the dates we want to run winter design storms for, so that we're consistent. For winter, it was January 18th to January 26th. And that really just represents
Well, that's the standard that's been used by Alcoasand. Basically, it's identified a time period during the winter time period that basically dry weather. So it's a place that's not influenced by the rainfall that was in that time frame.
Where do we have that?
That was within, Amanda provided a presentation on running design storms. And that information was within that presentation.
And I've dropped all the links to those presentations in the chat.
okay. Specifically, I found it under the July 21st, 2022. That was a 3WG presentation. I think that one was recorded.
Sure.
Because that will have an effect when you run these design storms, and for us to be standardized is important, I think, on that.
We do have a question in the chat. How do we address start and end dates for sweeping?
What?
Sweeping.
Yeah. Model does not include sweeping options. They don't need to make any changes.
Like street sweeping.
I don't think it's,
If you want to say that.
I'm not
please,
sure what sweeping is.
Straight sweep.
After street.
Oh, really?
Yeah.
But the models do not account for any sweeping, so you don't need to make any changes to
Okay.
those dates.
Yeah, that is for water quality simulations,
Okay,
how much pollutants build up on street level. And we are doing no water quality modeling here. It's all hydraulic and hydraulic. So
Yeah.
don't worry about changing those.
so at this point, I should have everything built into the model that I need to run the winter design storm for the 2-year storm.
Hot start.
Well, the hot start, because we haven't changed any modeling elements, the hot start doesn't need to be revised. It has been our guidance. And I can go through an example of creating a new hot start if we do have to change something.
If it's not needed, then don't do it. Yeah, keep it simple.
Yeah. Now, I would say, because we're using a hot start in this file, in this model run, and that comes standard, if I were to change one of the modeling elements, I believe we would come up with an error and it would say incompatible hot start file, something to that degree, and you would have to rerun
I
it.
recommend anytime you change any element or any representation, highly recommend a new hot start file is created and used for your simulation. But just as a reminder, what the hot start file does is it basically it wets the system. So it's basically representing flow that's occurring before your storm event happens to fill the pipes. Kind of let the system come to equilibrium before the wet weather events are occurring. You have to run it up the leaks. Yeah, it's not a long simulation. It's really only need a day or two. It just wets the system and kind of fills those pipes and gets the simulation ready.
So you recommend that for?
If you make any changes to the collection system or your hydrology or really any changes to the model, I would recommend that a new hot start file be created that rerun.
So I accidentally am running this for 373 days because I didn't change 2004 to 2003. So it's good, to see some of the issues you're gonna have to face.
And
I hit stop and it takes a while to reset.
This thing is not going to work because it needs to read all that data for those 373 days. So we could be sitting here for like another hour.
Okay, well, it would have run smoothly had I not made that correction there. So maybe it's a good point to shift over to.
Yeah, we can cancel this, like go to the task manager and cancel this.
Okay.
roll all the.
We just hit stop.
I did hit stop mute, but I think as he had said, it's reading through everything.
Reading through the files is gonna take its time to respond.
Here, I'll let you take over from here and we can run. Yeah.
We did this on purpose, so everyone knows that it's okay to make mistakes, and then you will make lots of them while you're modeling.
Okay, well, try to remember everything that Jake talked about, and what I'm going to be sharing is essentially the same demo, but making use of EPA Swim. The good thing about that software is that it is free of cost. And the bad thing is that it doesn't have all those beautiful graphics that you've gotten used to. But let's get started. What you're receiving from Three Rivers are two zip files. One is this zip file that is for the typical year. And then you receive another zip file that has the files for the design storms. At this particular point, what I would recommend is that since you are working with Alcosan models or some models derived out of the Alcosan existing conditions model, Alcosan has been diligently working on updating their modeling guidelines. Please reach out to Sam Chomsky to get a copy of that. It is going to help you guide through the naming conventions that you see with these models, and also some best practices that need to be made use of when you're making use of these models or making any changes to them. So that is something that I highly recommend. Let's get started. You go find your EPA Swim, open up the instance. Let's hope it doesn't make us wait another hour or so. In the meantime, let me try also unzipping the files here.
Paul, are you aware of any, their runtime differences between PC Swim and EPA Swim?
Well, the beauty of PC Swim is that it gives you a couple of options where you are making use of the complete processing power of your computer. So if you have multiple threads or multiple cores in your computer, you can go to the options and select that you want to be making use of everything that is available on your computer while you're doing the run. So with the selections that you make, it can surely impact the run times when you're making use of PC.
I tried running it on Amazon web server. Can rent their processing power. Both for the storage and CPU. Some people have done that.
Yep, we done that
Yeah.
for Alcosan too. So now we have the zip file opened. This is the folder. It is showing all the files that you have received that were listed under Brad's presentation. The input file and the output files that you received are in this particular folder, and then one level up is where all the input files are present that the model is referencing. As Jake pointed out, when you're working with PC Swim, the way it packages the model, it is already making correct references to the input files that the model is referencing. But when you're working with EPA Swim, this is the first thing that you need to be making sure that all the path references that are present in the model are correct. Depending upon where you copy your zip file and where you unpackage the zip file, those locations are going to be different from the time that the model was packaged on Three Rivers end. So that's the first thing that we need to make sure. You go ahead and open up your text file, the INP text file, that's the model input. And you can look at these locations. They are referring a particular D drive on some computer, but that is different from the location that I am working on my desktop. So I'm going to be updating these paths. There are two ways that you could be doing this thing. One is in the text file itself. And then there's another option that you could be doing it within the SWIM interface. So I'm going to show both ways for whatever level of confidence or comfort that you have working with these models. So these are some of the files that are getting referenced. You are making use of a rainfall file. You're making use of the inflows file, which is providing the time series for the drive of the flows. You're making use of a hot start file. You're making use of a climate file. And then the time series that you are making use of are under the time series section. So this particular model is making use of 4 different time series. One would be the downstream HGL boundary condition. One would be the flow, or maybe 2 of these are flow boundary conditions up in the system. And then if there's an outfall, that the outfall itself would have another river stage boundary condition. So the easy way is to basically know which folder you are working with, go to that folder, copy the path, and then go back to your text file and just update the path there. This is one way of updating the files. You can save it, close it, and let's do the rest of the work in the interface itself. So go to the interface, you're opening up an existing model. So you locate that model.
Oh, did you only change the path for the time series
I did,
and not the other?
because I want to show how the interface can also be used for making updates to the paths.
Under that, on the II. I'll let you change.
What did you do?
No, that was a time series section.
Yeah, there should be a section. Just for-
So if you're working in the text file, just open a square bracket and type in time to search for that section.
That same file does exist, you know, in the PC Swim package as well. It's just the input file. We're able to open the in a text box. And you know, that maybe that's the quickest reference to see. Yeah, there's all the.
I think I would recommend if you're not accustomed to working with the input files, you're probably better off doing it through the interface. So
Right, it's like I said, it's just the
if
comfort
you're
level.
comfortable with format, the layout of the input file in a Word or in text editor, sometimes that can be more efficient.
So this is what the welcome screen looks like when you're opening up the model and the interface. One of the checks you should be making is to make sure that the version that you're making use of is the correct version. So you go to Help and About, and here you can verify that the correct version of EPSOM is getting made use of. Right now, the way the model has been brought in, it doesn't seem to be showing anything in terms of information. So one way to do that thing is just right click anywhere in your window and go to options, and you can annotate the different things that you want to be shown in the interface. Maybe just selecting the node is just going to keep it clean, not get the interface a lot more crowded. But it helps you orient yourself as to what you're looking at. So this particular submodel extends between TO1 and TO5 POCs in Turtle Creek. The boundary condition as it ties into the deep tunnel interceptor system is at M61 DT. So this is one location where the hydraulic grade line boundary condition would have been applied. And then in terms of the flow boundary condition, looks like there would be two locations where boundary conditions would have been applied. One is this upstream terminus of the model, and then probably this one. So this is something that we can surely check if you double click on these nodes. If it says that it is making use of an inflows file, that means a boundary condition flow input has been included here. If you click on the three dots ellipsis there, it identifies which time series has been assigned as the boundary condition here. If you want to edit this, you click on that, and this is the place where you can actually make changes. Now, the thing to note over here is that I made changes in my text file, and the correct path is reflecting here. If it was not the case, then I could surely press here, go back to that same path, and make a selection once again. So this is the way you update the file path in the interface. Now, there were some file locations that I did not update in the text editor because I wanted to use the interface to show that thing. And those are the files that are actually were being referenced towards the top of the file. If I go here under options and I go to general, so it is giving you a couple of options here. First is just defining the general setup of the model. What are the different types of things that you want to be doing in the model in terms of routing options? Do you want to be simulating the rainfall runoff? Do you want to be simulating RDII, snow melt? And then what are the different infiltration methodologies that are available, and which is the one that you are making use of in the model? So as the radio buttons suggest, there is a single option that you need to be making use of in your model. It's not that you can mix and match things here. So there are occasions where you might, well, not in the Alcosan system, but others where you might run into a different methodology for modeling infiltration, but this is where you make that selection. There are a couple of options for routing methods. The Alcosan model is a pretty evolved model. It's making use of dynamic wave. There are a couple of other options for more simple models that you could work with a steady state or the kinematic wave options there. The date tab is where you are actually setting up your simulation options as to what is the period that you want to be simulating. For this particular demo, I'm not going to be recreating the hot start file. I'm going to make use of the one that came with the model. But one of the things that we want to be demonstrating is how do you extract overflow statistics from the model? Just to give an option, I'm going to set up a run for the first 2 weeks of July so that we get a couple of rainfall events, and we are able to see multiple overflow events showing up. So I changed the date to July 1st till July 15th. And hopefully I remember to change 2004. So it's going to run for 2 weeks. The time steps are what we make selection for routing purposes. So the Alcosan model, it is making use of a default 10-second routing time step. This is the time step that the model is going to be making calculations every 10 seconds during your simulation period. You could work with a smaller time step just because you are working with smaller submodels. But the recommendation would be to just keep the routing time step consistent with what you have received so that you don't run into differences when you are comparing results that Alcosan shared with you and what you're coming up with. The Alcosan models do allow for a modified or a changing routing time step depending upon the needs of the model. And those specifications are provided on this particular window. So if you look at this particular parameter, it is saying that, well, the minimum time step that we would allow during the simulation is half a second. And then to change the dynamic routing time step, we would allow the model to be making use of conduit lengthening so that it can converge quickly on a solution, but it's going to be working with a 5-second time step there. These are some of the parameters that help control how many iterations the model is going to be making before it converges onto a solution. These are numbers that have been optimized for AlkaSan. If you play around with this, it is surely going to be impacting the runtimes. Well, for the sub models, it's not a big deal, but for AlkaSan system-wide model, these are important parameters. Recommendation would be not to mess with them. So here is where the files are getting referenced. So like I showed before, there are 3 input files that are made use of during the typical simulation: the rainfall file, the inflows file, and the hot start file. Now, if you look at these paths, these are what you would have received from Three Rivers. So it's starting with a D drive somewhere. Now we want to be updating these paths to reflect your current machine. So you highlight that particular row, and then you go into edit, and it's going to open up this window where you get a chance to browse to your file on your local hard drive. Okay. It takes me to the folder that I want to locate my files. And it identifies the RFF file, which is a binary rainfall file for the typical year. I make that selection, and it updates the path for me there. Do the similar exercise for updating the inflows file location. And the hot start. So with that exercise, we have updated most of our files. There's another one that is lingering, which is the climate file. So you go under climatology and you click on temperature. This is the location where you get to update the path for the climate file. You locate the climate file, and by default, it should be starting from the very first day. But if you're running a simulation like I am running my simulation from the 1st of July, you could set that date here. Yeah.
We'll have to remember to come back and change it. So, find people forget to do that. It's better to leave it alone.
That's fine. Yep.
So if you left it alone, the model's gonna go to July 1st, the climate file, right?
That's the hope. I'm just a bit panicky.
Okay.
So it's to be sure I do
If
that.
there was an option, if they had a similar option for inflow file, that will be great.
Yeah.
But that's where it takes an hour to read that 2 GB inflow file. Climate file is small, it's quick, doesn't make much difference.
Oh, we do have a question in the chat. Oh, there's a question for the end. I'll wait till the end. Go ahead.
Okay. Well, the climate file, even though it's a single file that we are referencing over here, it includes a couple of different data elements that are mentioned in these options here. So it includes the temperature, it includes the evaporation factors, and it also includes wind speed. So these are the 3 different elements that are present in the climate file that you're making use of. The other parameters are something that are defined in the model itself. So it's just reading it from there. So once you update the path, you are good to run the model. So always a good exercise to save the file before you start running the thing. We set this thing up for 2 days, for 2 weeks, so hopefully it should go quick.
I would have put a documentation note somewhere, Khalid. Khalid is not very good at documents.
It's all up here.
So maybe while we're, even though this is in the end, while this is running, the question is, how do we obtain the GIS files for mapping of model subcatchment boundaries? Is this covered in a different presentation?
Yeah, unfortunately, the subcatchments, why there's a representation in the model, you can see on the screen now, the kind of rectangles that are representing those subcatchments. So unfortunately, those are not represented directly into the model. I guess to look at those, I guess maybe if you could put a request into Annie, and we can get with Alcosan and see if that is something that could be made available.
Is this just a layer? Because I know we have it on a couple of our explorers where you have the subcatchment outlines, and my guess is that means that it's at least a layer that's available for download from our private MDS ArcGIS online server. Is that what this is? Or-
What I would have to go back and look at those. There's
Yeah.
different versions of the subcatchments. I mean, there's the POC level that basically outlines what goes with their POC, like TO1. And then there's another version that breaks that up into smaller pieces or into the modeling subcatchments. Now, the one thing that is not available anywhere is where we have those multiple slope categories that I mentioned earlier. There isn't a coverage that shows where's the high slope, low slope, medium slope, or the intermediate ones. So that is something that's not available. But we can take a look to see about seeing what's on the MDS site or on the current mapping of Three Rivers to see if that provides us the level of detail that's needed.
Yeah, Annie, I'll be interested in that, the one you mentioned, because with a good question. And earlier when we were telling people that, hey, you can, look at the current condition of your subcatchments and see if they have changed. If they don't know how they were represented, how are they going to know how they have changed? So it's a good question. I also want to, take a look at that layer you mentioned on MDS. And maybe, that will be a good place to start with.
Okay, well, the run is done. And let's now go into the details of how the run progressed. This particular window gives you a quick summary as to what the continuity errors are for both the runoff as well as the routing. Alcosan models primarily are rather stable models, and if you're working with smaller sub models, there's the flow routing continuity error should be less than 0.5% or 1% for you to have a level of confidence in the results that you are generating.
Your guidance like that anywhere?
Yeah, I think Alcosan's modeling guidance document does go into continuity errors, right, Sam?
Yeah.
So
yeah,
that's a reference that I
It's something we can look at for the ad hoc committee.
Yeah.
With that information.
So now the last thing that I wanted to cover is essentially how do you look at the overflow results from your run. So you identify the link that you want to be working with. I am zoomed into TO1, the rear, for looking into the overflow stats. You select that thing in your interface, and then you go into the statistics functionality. I think it can be referenced from here as well, from report and statistics, but there's a button there that you can also make use of. So let's see, before I go into that, let's just plot it out to see how it looks. So you made the selection for the rear, you go to the graphing tool. By default is going to be picking the complete simulation period. but you can surely have a subset of it selected. And then you basically say press. So what it does for me is gives me a sense as to how many events should I be expecting to see when I start generating my stats. So looking at these numbers, at least 1, 2, 3, and 4. 4 events are what I should be expecting when I generate the statistics. Go back to your interface map here, and then go to summary. It is already selected the link because you made a selection of link in the map. It identified which link you're going to be working with. You want to be working with the flow of this particular element. You do want to be doing an event-based summary. But if you're just interested in the volume, you could surely make it something different. And then the parameter that you want to be working with for the flow link is the total flow. You want to assign a threshold value for Alcosan overflow stats. The standard is 0.1 CFS. So that's 0.0646 MGD. Alcosan makes use of 24-hour interval time for defining events. So you make those selections, and then you say,
There'll be some other standards we talked about, yeah. Yeah.
this gives you a quick summary, and the event tab lists for you the different.
I don't know what that.
That was an interesting way back.
Maybe they never see.
I guess I can always do this.
I don't know. Sorry. Oh, yeah.
Okay, so this summary is essentially what is listing the different events. When we were looking at the graph itself, it suggested that maybe we should be expecting 4 events. But then once we define the threshold, that would have essentially dropped one of the smaller events. So it is listing 3 events for us. So if you click on the rank header, it is going to select the complete table for you. Then you go to edit, and you want to copy it to clipboard. And then you open Excel. And paste it in Excel. So if you sum these 3 columns, sum these 3 cells up, is going to give you the total volume of overflow at TO1, which is 5.8 for those 2 weeks that we simulated the model for. If you are running it for the typical year, you can expect to see anywhere between 30 to 60 such events listed. You're going to be summing all those different event volumes to get the total for that particular overflow that you're working with. I think this is the end of the demo, but if you have any questions, can usually try to answer that.
No questions currently right now online. I know we're coming up on the 2-hour mark, so I appreciate everyone sticking with us. I also want to say, as soon as we get this uploaded on the YouTube channel, the link will be on MTS. I also dropped the link directly to our channel, so if you just want to subscribe to it, it just makes it easy to find. But
Hey, I just wanted to add one thing on to what Colin said when he identified the link. As part of the TMs that we provided on the percent captures, we identified the links that we actually use to calculate those volumes. So I would highly recommend that you go to those TMs, pull out those links, and those are where you calculate it. There's decisions like in there, you have the weir, you have the outfall pipe. There are different places you can grab it. They will get slightly different answers depending on which one you get. Sometimes there's backwater issues that make it difficult to quantify it. So, you know, I would recommend using the same ones that are within that TM.
And one final note here, like if you're running your model in SWIM, ESWIM interface, try to save the run. So when you go to closing the window, it asks again, do you want to be saving the simulation results? And this is, I think, the critical decision point that if you want to be saving your simulation results, you should always make that selection. Otherwise, your run could be lost.
That differs from PC Swim.
It tough.
Because PC Swim
Yeah.
automatically saves when you run.
Maybe I missed it here. I noticed Jake put a note in there. What he was running that one. I didn't see that occurring here. Remember, Sam, when you had said, he mentioned it.
It's in
Yeah,
the-
I said, Khalid, you forgot to document.
okay.
He said it's all here.
Okay.
Yeah.
Okay.
I think
So
that
you-
comment panel was in the bottom left, though, it looked like on EPA's. plan.
Yeah, it was different.
Okay.
Yeah, it's very important, documentation.
I don't know, Cole, the professor might be knocking a couple points on that.
Yeah, show all the work.
Right.
Can I stop?
You got this.
The- I'm gonna do the ending.
Yeah, so,
Right. Well,
we have that PowerPoint up there real quick.
Just in closing, a couple of things. Let me get down to the last slide. So just looking forward, obviously, one of the things we're looking for, if you see needs that you have from a modeling perspective or have questions, maybe you dive in. I only talked about pumps and said there's 5 different types. If you got questions on pumps, you can reach out to us. We'd be more than happy to talk through those. Or if you're running into issues in running your models, or if there's things that you think would be good to discuss in this type of workshop, please let us know. Obviously, your next steps are you need to be updating your models or reviewing the submodels that you get, seeing if they're truly representing your current conditions. If there's been projects you've implemented, obviously that's something that you may want to look at putting into those models and updating the models to reflect that. Then developing your alternatives to achieve your percent capture improvements, and ultimately developing that list of projects. That'll allow you to estimate the performance for those projects to see if you're meeting that 10% project. We will have the model revision template and guidance ad hoc committee. As we mentioned a couple of times in the presentation there's a number of things for that committee to look at, try to document, that could be the other things. If you want to see, hey, can you just get us a guidance document that would put this in so I don't have to go to 7 different presentations to track it down? We can get that into those guidance documents that we'll provide. Lastly, one is looking at different approaches for representing those source control projects, right? So if we're saying we're either trying to put in, projects you've already done or projects you're looking to do as part of your consent order, what's the best way to representing some of those? So I think that's one thing to look at. Alcosan has agreed to present some of their guidelines that they have that they use for GROW in representing source control projects. So that will be an upcoming meeting for them to present kind of their approaches for doing that. And then once we hear that, we can react to that, see if there's additional information we might need to provide. And by all means, we can then, add to that moving forward. So but that is what we have for today.
Thanks, Brad, Jake, Colin. I think it was a very good presentation, a lot to learn. I think what I've got out of it is maybe condensing some of the things that I talked about into maybe one report, so we're not looking at 4 or 5. The other thing I'm working with Annie, I know we talked a lot about stuff on the MDS. One of the things I struggle with on the MDS, we have a lot of stuff on there. So Annie has found other ways to share information. So maybe we'll pull something and just put up about this is what we use for modeling. So we're going to try to simplistic, but I think Brad hit on the key. We're here for you. We've created this great partnership between Three Rivers and communities and Alcosan. We're all really working together. If you have questions, please bring them to us. We can't answer them. We can't help you if we don't know what your problems are. Please just send Annie or I an email and we'll find the right people to get you the answers if we can. So thank you and we'll see you next month.
See you, Nate.
Thank you.